Welcome to the first panel session of day 2 morning, and I'm very happy that so many people are joining, even in their 9 o'clock in the morning, and someone is still sleeping in the hotel, but you're very enthusiastic to join the first session. Okay, so that my name is Taisuke Boku from University of Tsukuba and the JCHPC, and I'm running the older supercomputer procurement and operation, and also application development, system software development, everything for more than 30 years in my university. So I'm one of the long-time runner for the HPC system, every HPC system. So today's title of the panel is Commodity Interconnection Next Generation for the Next Generation Perspective on the Hardware and Software. So it is a really excited panel, I believe. And maybe I'm the most excited person here, so that this is, as you understand, there's an interconnection network is everything, and we cannot survive for the HPC and supercomputing AI without interconnect. So interconnect is one of the most important technology, as well as the CPU, GPU, FPGA, or any accelerator, and of course the memory. So, so that I don't like to take so much time. So yes, interconnect network is the most important for us. And so far, we have a lot of interconnection network in about 30 to 40 years of the history of the HPC systems. And the first beginning, there's only Ethernet from the 10 megabit per second. Young people don't understand what is a 10 megabit per second internet. Networking and 100, 1G, 10G, 4G, 40G, and 100G, and more now. And after that, in around 2000, there are many of the so-called system area network, or SAN, like Millinet, or CSI, and others. And after that, InfiniBand occupied the world. So that everyone knows that more than 90% of the top 500 machine is occupied by their, equipped by their InfiniBand, by the former Mellanox, now NVIDIA. But always we need some alternative solution, because if there is no competitor, just to keep around and they decide everything, and even the performance limit is decided by them. So we always require there some alternatives. For example, not just the Intel CPU, but also AMD CPU or NVIDIA CPU and something like that. So what the focus on in this panel is that, so I invited the 3 panelists here. So from NVIDIA, former Mellanox, Gilad Shiner, he's a top engineer of the InfiniBand and the other NVIDIA-related interconnection network system. And what is current position? Of course, everyone knows that the InfiniBand is the most important interconnect for any of the HPC AI supercomputers. But then what is the next? Or can continue to be a champion or not? And the second one, the second panelist is Thorsten Hofer from the ETH Zurich, and tentatively also you're Microsoft, right? And he's a new hero for the leading discussion about the Ultra Ethernet. So today's one very big new topic is Ultra Ethernet, and he's leading the discussion. And maybe this is good to the HPC AI for the next generation, or how Ultra Ethernet can beat the InfiniBand technology domination of the world. And they two are mainly for the hardware and the lower level technology. And also I invited DK Panda from Ohio State University. Everyone knows that, and he's a developer of the MBAPIT 2 system, and that is one of the most famous and used open source MPI stack, and we cannot survive without an MPI. So he's a software side. So what I'm expecting here is that theoretical fight, not a physical fight, okay? I especially asked to the Gilad that don't do anything. Unfortunately, he has a microphone here, so that I'm really worried about that. So he refused to put this microphone. He likes to have his some arm. so I will watch him. Anyway, so that there are two sides of the technology for the most important technology for the interconnect of the supercomputer, and also the DK is a kind of the judgment Okay, so I'm very curious that which he preferred, or both, of course, and something like that. And finally, I'm the moderator. So let's start the talk, but, oh, sorry, just the same slide. Oh, okay, so the panel discussion consists of my 5 minutes talk. It's already past the 5 minutes, so I will stop. And 10 minutes for each, or the three panelists. So the first one is Jedat China from the NVIDIA. And he's an InfiniBand guy, so he's a defending champion here. And the second one is Torsten Hoffer. He's a challenger to the new world of the interconnect technology. And finally, the judgment is go to the DK Panda. So these order, 10 minutes for each, and we have a remain of the 25 minutes. So have any free discussion, including everyone here, and of course on stage. So that's it. So thank you very much for coming. Okay, let's start. China.
Can you, yeah. So before you start my 10 minutes, one thing that I try to do today is compete against DK Panda. Okay, that's the real competition, because DK Panda typically come with 10 minutes and 60 slides. So I decided to try and beat him on the number of slides. We actually have around 19, give or take, and I said, I'm going to win. He came with 23. So I lost the first battle today, right, on the number of slides with DK. The second thing is Professor Boku here actually wants to see some fights, and Torsten came with a red T-shirt, red shirt. You cannot see blood stains. They give me this mic as a weapon, and there is glass bottles here, so I'm going to surprise you guys. We're not here to fight, okay? We support a lot of things. So now we can start at 10 minutes, try to... I lost on the number of slides anyway. So. Okay, so what we do in NVIDIA, we build a data center. And the reason we build a data center is because the data center is the unit of computing. It's not a CPU or GPU or a server. Today, the whole data center is one unit. And designing that one unit requires essentially a lot of infrastructure. It's not just a single network that connects everything. Now there is multiple networks that require in order to build that AI infrastructure. There is the scale-out network, or what we prefer to call it as the computing infrastructure. And on the computing infrastructure, we actually provide two options. One of them is InfiniBand, and the second one is Spectrum-X Ethernet, and I'm actually going to cover both. There is the scale-up network, where we use NVLink for. And the difference between them is that the scale-up network targets to create one GPU. So there is a lot of GPU ASICs, in a sense, and the scale-up network is there in order to make those ASICs become like one. And that's why when we look on NVLink 72, it's like that is the unit, that is the GPU. The rack is the GPU, not just the ASICs. The scale-out network comes in order to connect all of those racks together and actually create the compute that is needed to run different kind of missions. Another infrastructure is north-south. It's the user access, and this is where we use DPUs in order to separate the infrastructure domain from the application domain and enable secure access into the data center. So there's multiple infrastructure that actually build that single unit of computing. Now, this is how LLM looks like, for example, from an infrastructure perspective. There is compute cycles that are running in multiple iterations that are repeating themselves, but now actually the entire infrastructure is part of that computing that is running, or part of the training. There are multiple operations, there are collective operations, there are point-to-point operations, they're running on a scale-up infrastructure, they're running on a scale-out infrastructure, and it's very much bursty. So you need to have an infrastructure that supports a high burstiness of traffic. You want to eliminate jitter, you want to eliminate tail latency, all the stuff that we already know on running scientific computing. Now, InfiniBand was born in 1999, so it's 26 years in the making. Every year it was told that it's going to be the last year of InfiniBand. Unfortunately, it's still running for 26 years. And it was built for distributed computing. It was designed specifically for distributed computing. Focus on RDMA, not focusing on any other thing. Lossless, so you don't drop packets and you don't create retransmissions. Adaptive routing that was evolved over the years. So InfiniBand didn't stay still since 1999, but over the years there were more and more features being added. So we have full fine-grained adaptive routing. There is congestion controls to eliminate noise, eliminate congestions, and so forth. InfiniBand still today is the gold standard. Any systems being built, any network being designed, even our own networks, are being compared to InfiniBand. And the reason it's being compared to InfiniBand because InfiniBand is the gold standard. This is where you can get the maximum performance on it. It's a network that does not actually make sure that every traffic is very efficient and you can use the entire routes to the maximum, but it also was the first network to bring in-network computing. And the ability to run reductions on the network, and actually those engines were evolved over time from just doing simple reduce operations to do multiple operations, and now they're doing reduce scatter or gather, and so it continues to evolve with the introduction of new frameworks, both for training and for inferencing. So that combination is amazing from that perspective. The latest generation of InfiniBand, which is XDR, running 800 gigabit per second, is now being introduced with Blackwell Ultra that's coming out of the GB300 systems. The switch has 144 ports of 800 gig. The SuperNIC support PCI Express Gen 6 on it, and it's a full end-to-end on 800 gig per port that goes from the NIC, and then the switches can drive it throughout the fabric. Low latency, the new switch actually has different ports, a separate port for management, so you can actually monitor the entire fabric without using any ports of the network and manage and configure that. And with that 144 ports, you can actually build more than 10,000 endpoints with 2 tiers of fabric. You can go to 3 tiers, and essentially it's become unlimited on a size. You can do oversubscriptions and so forth. So InfiniBand is the gold standard, and everything that exists or everything that we actually develop, we compare to InfiniBand. Now, we needed also to look into Ethernet, and the reason is that we see that AI is going everywhere. And AI is going everywhere, means every data center is going to run AI, which means that AI is going to go to enterprise, and AI is going to be used in clouds. And those entities are very familiar with Ethernet, and they build their software stack on top of Ethernet and the management tools on top of Ethernet. And they need to leverage the Ethernet ecosystem from the software perspective, and therefore it would be better for them or easier for them to run Ethernet for their infrastructure. And for that reason, we created a new kind of Ethernet. And the reason that we created a new kind of Ethernet, because everything that exists in the market today was built for the hyperscale clouds, single server workloads. It was not built for distributed computing. It's lossy, you can drop packets, it's fine, jitter is okay, let's run flowlets and stuff like that, or use deep buffers, which is actually your enemy. And therefore, we needed to create something else, and we create SpectrumX. And what we did in SpectrumX, it's actually copied the elements of InfiniBand into Ethernet. So we enable lossless on Ethernet. We brought the full focus on RDMA on Ethernet. We brought the fine-grained adaptive routing into Ethernet. We brought the congestion control, the telemetry-based congestion control Ethernet. We actually copy a lot of elements that were evolved over the years from InfiniBand into Ethernet, into SpectrumX, which in one side, it's like the first Ethernet for AI, but on the other side, it's not the first generation, because it has so many generations of InfiniBand that was built into SpectrumX. So we were able to achieve great performance. You can see there, eliminating the tail latency compared to any traditional Ethernet that exists out there. Great elements across everything. So improving the effective bandwidth on the fabric by 1.6x, going to more than 95% effective bandwidth across the network. The tail latency, the noise isolations, making sure that one job cannot impact another job when you're running on a cloud. So the great element of SpectrumX, we built a digital twin, so you can actually build your infrastructure and test it and run it before you build the physical data center. And one of a great example is xAI, which is a public example. They have built more than hundreds of thousands of GPUs, more than 100,000 GPUs running in a single data center, running a single workload, and running on Spectrum-X. And Spectrum-X is the only Ethernet that was able to achieve this scale. There is no other Ethernet that is running at that scale, not even close, for a single job. And now it's going even beyond 100,000 GPUs. So it's a great element that we brought into Ethernet, into Spectrum-X, to achieve that zero collisions, to achieve the effective bandwidth across the fabric, to achieve that amazing scale, running single workload. And the next step is going into co-package optics. Okay, as we see the scale, we see the bandwidth, the distances require optical connections. Optical connections consume a good amount of power. It can consume around 10% of compute power. There is a lot of elements that you need to build in the data center which impact the resiliency of it. And this is the time to co-package optics, and we announced co-package optics infrastructure. Essentially what we did is we moved the silicon engine, the optical engines from the transceiver into the switch package, and by that, first reducing power consumption by around 3.5x. So it's a good saving on power, which is the limiting factor today building data centers. The other element is increasing the signal integrity, because now you don't need to manage the signal all the way from the optical engines on the transceiver through all the elements to the switch. Now you can do it actually very close to the switch. So the signal integrity is better. We announce NVIDIA Photonics, so bringing co-package optics into InfiniBand, bringing co-package optics into Ethernet, with a big ecosystem of us to develop new innovations around that technology, from a packaging perspective, into the optical arrays, into the engine itself is built on microring modulator, and so forth. And with co-package optics, I'm going to take 10 more seconds. With co-package optics, actually you can reduce, or for the same ISO power, you can put 3x more GPUs. And then reducing the amount of GPU or components in the data center, which increase the resiliency of it. And we introduced both co-package optics on Ethernet. There is two different switches. One of them is 100 tera, the other one is 400 tera that is coming. And on InfiniBand, we will see systems coming very shortly, in a sense. We're going to see several systems coming out with co-package optics, which is the next level of innovations, I believe. And with that, thank you very much.
Okay, Torsten, please.
Okay, thank you very much. Well, before you start the timer. Yeah, thanks. No, it's still setting up. Thanks, Gilad. Great talk. I mean, you immediately decided to go into close combat, so you talk about InfiniBand and Ethernet at the same time. Yeah. And I didn't define whose blood we will see on my stain chart. We'll see. And yeah, thank you very much. My name is Torsten. I'm here to take the Ethernet side, and we'll see. So first of all, Gilad already mentioned it, the Ethernet ecosystem. The Ethernet ecosystem is a gigantic size ecosystem. And let me illustrate this a little bit, because what is the Ethernet ecosystem? Actually, I want to quote Ram Belaga here, the SVP of Broadcom, one of the largest companies in this area, that are building most of the chips in that area. So it's not NVIDIA. And he says that Ethernet is shipping 600 million ports annually. If you think about that, how much is that? Well, that is actually a true instance of high-performance deployment, because they do deploy 20 ports per second. While I'm speaking here, 20 ports, 20 ports, 20 ports, 20 ports. Right? That is the volume of Ethernet that we are seeing. But now, Gilad already talked about it. Ethernet is not the same as Ethernet. So there is Ethernet, and then there is Ethernet. There's the Ethernet we have in the data center, and then there's the thing that Gilad called Ethernet, which I would really call IB over Ethernet, like he already said. It's for weird reasons. It's called RoCE. RDMA over converged Ethernet. I could go into details, like one of the biggest misnomers you can imagine, but it's really take an InfiniBand packet and strap it on top of an Ethernet packet. It couldn't be more efficient than that, right? 48 bytes to Ethernet packet, and just strap the full InfiniBand thing on top of it and see how it works. Well, that is a bit of the issue, parts of the issue with the backwards compatibility. Also, when you go for this RoCE thing, people are you're immediately losing all of the nice benefits that Gilad mentioned, so you're basically not having any of the adaptive routing features. Any of that is just not available in the Ethernet ecosystem. So now, We could look a little bit more at the workloads that we're expecting. I don't want to go into too much detail, but there are two workloads that we're talking about here. Gilad mentioned LLMs. I also want to bring HPC into the business here because we're at the ISC conference, ISC HPC conference. So we're trying to support both high-performance computing as well as AI systems. You can look through this yourself, what the difference is between those workloads. At the end, they're married at the hip, so to say. All of those are essentially bulk synchronous applications. All of those are running in lockstep, more or less, and all of those have the feature that the final arriving rank or the final arriving process, or whatever you want to call it, is actually determining the overall performance of the system. Okay, so what we try to do, or what we actually did, and you'll hear an announcement very, very soon, that unify those two, high-performance computing and networking in some sense. You could argue, well, as Gilad just did, isn't that already Rocky? Well, I already mentioned Rocky is not sufficient for that purpose. We actually wrote a paper on this in case you care to go through the whole details. I only have 10 minutes. This would be a 30-minute talk to go into all the technical details. I mean, it's great that Rocky is lossless, yes, but there are congestion trees, so you will affect other flows. It's great that Rocky is lossless, but just because of the losslessness, you need extensive switch buffering. It's quite expensive to build. There are many, many, many other features that I could talk about that would be complicating the deployment if you're a real data center provider. This is why data center providers, many of them don't necessarily like it. They have to buy it because it's the only chance you have today to build a large system like the XAI system. There's just no other thing available that you could deploy today. But we try to change that. So together with a bunch of companies, we went together, I don't know, it's like 6 or 7 founding members, and I'm one of the people who was originally involved. And we came up with the idea to take Ethernet, to lift it to the next level, and really, well, create a competition to the 26-year-old specification. Like, go back 26 years. When InfiniBand was designed, we had about 1 million times less compute or cost, or 1 million times higher cost per transistor, so 1 million times less transistors. The bandwidth itself didn't grow by 1 million times from there to now. So the ratio between available computation on the chip and the bandwidth the chip needs to deliver changed drastically. We have much more computation today than we had 26 years ago per megabyte per second that the chip is going to deliver. So that's a much longer talk. By the way, on YouTube, I have a 1-hour talk on Ultra Ethernet in case you want to know all the details. And in my remaining 5 minutes, I do not have that much time to go through all the details. But that's the fundamental observation. We have much more compute now. We really can change the hardware for once. If you stick to this InfiniBand specification, you'll most likely not be able to take advantage of this. So what happened today? Ultra Ethernet is pretty big, 10 steering companies, 18 general members, 25 contributor members, including NVIDIA. So this is how it looks like. By the way, what's my role? I am the chair of the biggest working group, the transport working group. The spec is about 600 pages, and transport is, I believe, more than half of it. So it is mostly a transport specification. There's a very large team. It's free to join. In case you want to join, please look at the webpage and come. 1,300 people participating in the thing, so it's not easy to manage. So now let me compare a little bit classic RDMA and Ultra Ethernet. So, I mean, lossless, we already heard it. Ultra Ethernet is lossy, because it's much easier to manage a lossy network in a data center. In-order delivery, mostly, if you talk about Rocky, full out-of-order delivery, it's really like InfiniBand in the sense, the Ultra Ethernet, while in Rocky you lose that property for any deployment that I would know. We have proprietary congestion controls, like many of those are published, but still try to hook them up to some other vendor. Ultra Ethernet has open single-path routing versus multi-path routing. I don't want to spend too much time here. Very large state per queue pair. There's at least a kilobyte state per queue pair in any of these systems that I would know. In the Rocky system, Ultra Ethernet has the completely, oh great, yeah, Microsoft, thank you. Oh no, actually, it's just for me. Ultra Ethernet has a completely open, I go to that thing here. Yes. Ultra Ethernet has a completely open connectionless API, and actually that thing doesn't work anymore. No, it does. And security, very important. Security is a more complicated topic. I would need about an hour to explain how you can break Rocky open in kinds of various installations. You can read those papers and you'll understand how to break it. In Ultra Ethernet, we basically avoided all of that, and that thing goes crazy, but yeah, avoided all of that. So, wonderful. And we are back. No, we are not. I still need to click twice for every single thing here, at least. Okay, cool. So now, let's go a little bit more into detail here at the, how does it actually look like? So at the end, we want to support applications. We run applications over the thing, and this is the applications you know and love, MPI, Nickel, or any collective communication library, RICL, ECL, whatever you want, and of course, OpenSHMEM and many other applications. So at the very bottom, the whole thing, Ultra Ethernet, it's called Ultra Ethernet for a reason. It's Ethernet compatible. You can deploy, or you can use any Ethernet PHY. Typically, we would be talking about 100G or 200G lanes. Then comes the data link layer, which is also largely Ethernet compatible. So it's a standard Ethernet frame, as you can see there on the right. There are extensions. There is credit-based flow control, and then there is link-level retry. In fact, credit-based flow control is exactly the same thing that InfiniBand is using. It's not the same thing as Rocky is using. Rocky is using a feature that's called PFC, Priority Flow Control, which is kind of like a cheap, not so good version of credit-based flow control. So we can talk about that in detail. We have a network layer. We have lots of headers. The network layer is just IP, so it's fully backwards compatible if you're deploying things, like you go to the old textbook. And then the new thing is all about transport. We have semantics, we have a packet delivery subsystem, we have a congestion management layer, and we have a security subsystem. So these are the whole things. I have about 2 minutes to summarize all of those, and so I'll go rather quick, and then we can talk a little bit more about this. Semantics layer basically hooks up to the RDMA semantics on top. It's very much the same as you would expect from any RDMA interconnect, send, receive, read, write, atomics, all of that stuff. It defines nice protocols. It defines a rendezvous protocol that you can run mostly in hardware. It defines a protocol that is similar to a rendezvous protocol. It's called deferrable sends, which is fully implementable in hardware. You can actually fully implement a Nickel-like API in hardware with that feature. It's quite nice. We have 3 profiles, basically, AI base, AI full, and HPC, depending on your vendor. Do you want to build a very small NIC? Then you make an AI base. Do you want to build a more useful, slightly larger NIC, AI full, or do you want to build the full HPC NIC? Then you have the HPC profile. So there will be different products falling into each of these 3 categories, and there is a compatibility matrix, of course, for those. Then if you look at the packet delivery subsystem, that's actually super cool because it has fully dynamic connection set up. There is basically no connection state, and it's really nice because connections are set up at 0 RTT. So it's the first high-performance interconnect I know that you don't have to have any kind of handshake or so. You're basically, if you compare this to TCP, you have a 3-way handshake. Everybody knows this. Ultra Ethernet just has a single message, and the connection is there in nanoseconds. So that's quite nice. This means you basically don't need any state at the endpoint, and you have an extremely fast startup. And with that, by the way, you can support millions of endpoints, so that's also quite nice. Congestion management, I don't want to go into too much detail. It's actually slightly more complicated. I mean, there's a sender-based congestion management. There's a receiver-based congestion management. So if we compare to InfiniBand, for example, it is all of the implementations I know are truly sender-based. So we have a combination of sender and receiver, if you want. They do work together. They support multipathing and all kinds of cool stuff. There is a full paper on this in case you care about the academic parts. This is the sender-based algorithm, fully evaluated in an academic setting with lots of simulations. But again, I have not enough time to talk about it. The transport layer features for the security, there's a lot. It's fully scalable security. So there's O of 1 key state. InfiniBand has O of n key state if you do, because it runs over IPsec. I'm sorry, Rocky, if it runs over IPsec. So that is not scalable to begin with because you have to have n connection identifiers at every single endpoint. If you have 1 million endpoints, well, that's going to be a problem. But hey, who cares about security anyway? Well, mega data center providers do. So it has extremely high scalability in that sense. And with that, I want to come to my conclusion. So Ultra Ethernet is a wonderful open ecosystem. There are no products yet, because actually, watch today, 7 a.m. PST, something's going to happen so that may be related to a potential release of the first specification. And so we are an open forum. You can join. I talked about the details, what's going on. I can talk about more details after 7 a.m. PST. And yeah, in case you're interested, talk to me. I'm one of the people driving that stuff, and it's a lot of fun, I can tell you.
Thank you. Okay. DK, please.
Yeah. Good morning, everybody. So as Taisuke indicated in the beginning, it will be a fight, but I don't think it is going to be a fight as of now. So my role is a little bit less important here. But the more important at what I'll try to show, we have been in this field. Many of us have been almost for like 30, 35 years. Always, every time, the same question comes, okay, what will be the next generation interconnect? And we have been doing that, at least for me, when InfiniBand started in 2000, I have been involved. Prior to that, I was involved in Myrinet and Quadrix and all. Every year, I get the same question, okay? Will Ethernet take over? What will happen to InfiniBand? And same thing we are repeating. And I'm sure another 30 years, we'll have the same panel, okay? But the thing is, the things are changing. And then a quick note to Gilad. I know he always complains that I present a lot of slides. But my slides have a lot of performance numbers, concrete performance numbers, okay? So these are data-driven presentations, okay? So what I did yesterday night, I looked at the top 500 chart over the historical things. Of course, there are historical charts. I plugged out those numbers, trying to see. I started from 10 years back, 2015. And these are the top 500 numbers. If you see what, there are two, you go through the interconnect family share percentage, and gigabit Ethernet and InfiniBand. Those are the two data I looked at it, and you see the thing, what is happening here. So prior to, if you start from the left-hand side, of course, InfiniBand came. I have not included all those data. So that was the HPC domain, and the latency was very important, so that's why Ethernet was very low. And then what happened, this is the time frame Rocky got adopted. Okay, like initially it was coming, and Rocky tried to reduce the latency compared to the traditional Ethernet. So that's where you will see that the Ethernet started rising, okay? But then you will see in the in-between period, there was this ups and down, Ethernet went up, and then InfiniBand went down. But then in 2023, a change has happened again. A flip has happened, and this is primarily because of the bandwidth constraint. Earlier it was latency driven, but now with all these AI workloads, the bandwidth is becoming very important. Okay? So that's why we see here, so now there is a divergence between these two, and then the question is, okay, what is going to happen in the next 5 years or 10 years? Will there be a convergence, or will they come out? That's what we need to keep in mind. But then if you take a look at, let's say you are an end manager or somebody who is trying to deploy a large cluster, what are the kind of the major factors? You need to decide, of course, the features. All kinds of features are there. Both Gilad and indicated about the InfiniBand, Thorsten indicated about the high-speed Ethernet. Of course, there is a performance, scalability, stability. That is also important. With newer technology, it takes some time for it to be stabilized. Ease of use, a lot of people actually want. I mean, it's out of the box, it should run. So that's why when some new technology comes, it takes some few years for it to be stabilized. Of course, the cost matters. The cost is also important, but of course, that is a business decision. Persons like Gilad decide on the things. I don't decide on those costs. It changes the market dynamics. If one technology is significantly cheaper, okay, let's say a ultra-fast Ethernet comes and they will start selling it for free. I am sure the market will change totally, okay? Or Gilad decides to cut down the pricing by 10 factor of 10, it will change, okay? So those are kind of a market dependent, but let's try to see what other things are happening, and we are not seeing that market interconnect cost is going down in the recent years, okay? It has been rising up, and that's why people have been asking all these questions. But more important out of all this thing is the software ecosystem. So I'll call it like it is the software stupid. That's what matters. And that's what I have been doing over the years. And I'll try to show how we are trying to address these issues of different interconnects, trying to deliver you the best performance for both HPC and AI workload. So if you take a look, I think Gilad has touched some of these things. So you want taking advantage of all these heterogeneous resources. Of course, communication performance matters, point to point, but this is the collectives. Now, of course, all these collectives, those of you who have been working both in the AI world or in the HPC world, these are all reduce, all to all gather, reduce, scatter. AI world is somehow discovering that. But HPC world has been working on that for the last 35 years, okay? So any system, doesn't matter, whatever interconnect you bring, whatever system you put it together, if you deliver the best performance for collectives these days, that's what you win, okay? Of course, the cost constraints and all those things are there. You need scale up and scale out. So then to address these issues, because there are all these different interconnect, the question in my group we have been addressing, can we design a vendor-neutral software stack, okay? So that means it will work for any combinations of CPU, GPU interconnects, while trying to deliver the best performance scalability, Okay, that's what we can control. I can't control the cost, but based on the features, we can take advantage of those features and deliver the best performance and scalability. And that's where I'll be talking a little bit two of these projects. Many of you must be familiar, the MRPs project. This is where the high-performance MPI started. But now the second part is more important. I'll go into a little bit more details. We are trying to design MPI-driven converged software stack. Okay, so it is not the hardware is converged, but now the software is converged. So on the same stack, you can actually run your HPC workload, AI workload, big data workload, everything you can run. Because what matters for any of these workload, you want to deliver the scale up and scale out. Okay, and that's what we try to deliver through the point-to-point and collective communication. So I'll start with the MRPs first, and then I'll go into this ideal project. So those of you who are not familiar, we started this work almost day one of InfiniBand, from the Mellanox Voltaire days. When InfiniBand got introduced in October 2000, our group was the very first group in the world to come with a high-performance open-source MPI library, and we demonstrated it at the Supercomputing 2002, almost 23 years back. So since then, I'm very proud of my team. We are continuing this project almost now for 24 years and counting. And now we, of course, support all the interconnects. You name an interconnects, we support that. More than 3,400 organizations in 92 countries are using it. And just from OISU website, we have crossed 1.9 million downloads, just from our website. It is also a part of Red Hat, SUSE, OpenHPC, SPAC. We don't keep track of that. And as a part of this, we also have this OISU micro benchmark. So we enable people actually to reproduce those numbers, okay, and try to see which interconnect performs what. And in the beginning, when we started, we had here, if you see all the networking technologies, all the CPUs, GPUs, we had MPI and also PGAS. Now we are trying to combine at the upper level HPC, the machine learning, and big data science. So this is how our rationality look like. If HPC is able to take advantage of MRP's library, why not AI or big data? So in that way, if we can bring that converged software feature, it will actually provide you the scaling, portability. It will also provide that vendor neutrality. If you take a look at it very quickly, 3 kinds of CPUs, 4 interconnects, 3 GPUs in the market, anybody can deploy a cluster out of this, like a 36, one out of this 36 combination. So who will provide kind of the high-performance communication stack? And that's what we are trying to do. So this is our latest release. Some of you who are on our mailing list would have seen, 2 days back, we made this release. So what we do is we have the base MPI, and then we have all these modules which are down there. So you can think of the base and then the plugins, like MPI for DL, MPI for QML, MPI for Spark, etc. So here I'll show you some sample numbers. That's why Gilad, the more number of slides get added. So here I have taken 3 combinations, like a frontier system, which is AMD CPU, GPU Slingshot, then Vista Attack, which is Grasshopper, InfiniBand, and then the new thing, the Cosmos SSJC, which is the AMD MI300 APU, and then the Slingshot. So here if you see, this is the frontier, is the Cray. Cray MPitch is the MPI library, and we are comparing that with our MRPitch, and you see some of our latency, lower is better, some of the bandwidth, higher is better, so we are able to beat Cray MPitch there. This is for the collective and the AI workload. GPU already used, you can see. This is an AMD system, so there is a RICL collective library. So comparing with Cray MPitch and RICL, we are able to even deliver better performance here. So on the Vista Attack, so these are very latest number with 128 GPUs. So here you see the similar kind of things. The very bottom line, you will see the black line, which is MPI is able to beat both OpenMPI and also the Nickel. There are 2 different versions of Nickel. And this is very latest number with the Cosmos at SDSC. So this is the APU. So we have been able to optimize our MRP stack for the APU. And here you will again see these are some latency numbers, for the all reduce. So if you see almost 32 nodes with 4 GPU and 128 GPUs, we are large message sizes, we are able to beat by almost 86%. So then with respect to AI, so what we have done, I'm sure many of you are familiar with the torch distributed, deep speed. So what we have done, actually changed that stack to link to the MPI layer. So in that case, you don't need any Nickel or RICL or any of those collective libraries, but at the same time, take advantage of it. And here you see some performance on the Vista. Compared to Nickel, you see we are exactly able to deliver very similar performance, even a little bit better. okay, without using nickel at all, because MPI has the same exact performance, and this is the number on frontier. That's very similar. In fact, we are able to beat RICL here, because the RICL, we see that not heavily optimized compared to what at the MPI layer we can do. So with this, let me conclude this. So what I mentioned, the next generation interconnects, of course, have to provide features, performance, and scalability. Needs to be cost effective. That is the most important thing I think the community is facing. But at the same time, the converged software stacks like MHAPIs are needed, so that people have a lot of choices, so that you are not linked to any provider like a vendor-locked solution. So this provides end-user organizations to select and interconnect with the reduced cost and deliver the equal or better performance. So with this, I'll stop here, and we'll be happy to take questions later on. Thank you.
Okay, thank you, all three of you. And we have about less than 20 minutes, but first, I'd like to take any question, specifically for each talk or all of them, and then we discuss. So is there any question from the audiences? I cannot see oh yes, here. Is there a microphone, or do you have any microphone system? Yes, okay, please. And please identify yourself.
Hi, my name is Hari Subramani from The Ohio State University. Question is for Torsten. Hey. So on the transport, you mentioned that we are able to, with Ultra Ethernet, you're able to establish connections more or less on the fly. How does this compare with dynamic connected? Is it same, or is it able to reduce it even further than what DC is able to offer?
It's, I mean, of course, you have to look at the implementations once they come out, right? Because dynamic connected transport is an actual implementation. We have a protocol. I strongly believe that the protocol that we have enables a faster implementation, right? So because the protocol itself is extremely lightweight, it's designed from the beginning and not added later to an existing connection-based protocol. That it's a fast connection establishment. So everything is carried in the first packet. Actually, it's not even carried in the first packet. Even if a packet comes out of order, even if the second or third or 15th packet comes first, it's going to establish a connection, and then it's going to do the whole out of order thing. So it's actually quite nice.
Sure, thank you.
So it'll be faster, I think.
Thanks.
If well implemented.
Any other question? Yes, please.
Hi, thank you for your great presentations. My name is Shaha. I'm the CTO and Live Director of Toga Networks. So recently we're seeing a trend on the AI for the scale up. Many new protocols are coming over there. Do you see this trend coming also for HPC workloads, creating like small clusters for faster communications and better, improved collective communication over those fabrics?
Question for everyone?
Yes.
Okay. Maybe Dick
Yeah.
first. Yes.
Yeah, these days, if you see, the market is being driven both by HPC and AI. In fact, the AI market is much more larger now compared to even HPC. So whatever technology comes, let's say the NVLink or Ultra Ethernet, like the new solutions are coming, like a scale-up Ethernet and all. Whatever technologies will come, you can take advantage of that for the HPC workload. So in fact, in the MHAPIs, we optimize even within the node. These are, if there is an NVLink, collectives happen much more faster. So any HPC application can take advantage of that.
Any additional comment? Yes, please.
I think the answer is clearly yes, because HPC is just going to assimilate everything we give them, right? So and what we can give them in the local interconnect area, or what people call scale up, is a completely different environment where you can actually have different protocols and much optimized protocols. As we are seeing with NVLink, it's a great product because they actually trimmed the protocol to something that is running really well in a limited scale context, right? And that makes it very, very powerful and makes it very low latency, very cheap to deploy. Well, cheap, it's a business decision whether it's cheap or not, but, but at the end it would be very cheap if it was an open ecosystem.
Gilad, anything?
Yeah, so first it was kind of interesting that this panel has become Ethernet versus Ethernet. Because it was, Rocky versus UEC, so now it's Ethernet versus Ethernet, and there is other Ethernets. So there's so many flavors of Ethernet out there, and I'm not sure if you call it still Ethernet, because Ethernet of 10 years ago, it's not the Ethernet of today, and there's multiple different specs with different wire formats that actually don't talk with one another. So it's kind of interesting. Now on this,
well, one is called converged Ethernet, by the way, and the other one is real Ethernet, like old
you can call
Ethernet.
it whatever you want to call it. I also heard some proprietary networks on top of 100 least being called Ethernet too. That's why DK has that graph. But let's leave it aside. If we were called InfiniBand Ethernet 20 years ago, we were not even talking.
Oh, so first, let's conclude the question. Before fight, okay?
Some fight. By the way, DK said that we didn't have a data-driven slides.
Okay.
He started. So on the scale-up, actually, there is NVLink, for example. It's a great example, and NVIDIA did announce NVLink Fusion, which means that you can take your own CPU or different CPUs or your own accelerator and actually connect that to the NVLink fabric. So the answer is yes. If you would like to take multiple compute engines and make them like one, which is the essence of what scale-up is, then NVLink is an option that one can use. There is other attempts in the market. I think there is a U-Link consortium, for example, that try to specify one. I think UEC is trying to specify one. And I think there is one of the UEC members that contribute a different spec to OCP that trying to do. So there is multiple specs in kind of building or build up. Maybe used for HPC, the answer yes, including NVLink or any other option that will come in the future.
Okay. Can I add something into what Gilad just said? So
please.
The next one is for Gilad and Torsten. Gilad just mentioned we have UA-Link, we have NVLink, we have SUE, and we have UEC. We have many protocols trying to define currently the scale-up. On the Ethernet side, we are also seeing some convergence. We see the UEC right now. No product yet, but I know, by the way, Torsten, we do have AMD Pensando with UEC 0.75, but so anyway, we see a lot of new protocols coming from different places, different companies, and we see such a trend of divergence. How do you see the next few years if eventually we're going to have like 5 or 7 different protocols that do not communicate with each other? So.
Well, can I take that? Yeah. Well, one of the fundamental driving principles in UEC, in the consortium itself, was that we wanted to be true old Ethernet. So the requirements for the switch that you can employ, for the infrastructure that you can employ, are minimal. You only need ECN. That's every switch has that. And you're basically otherwise standard Ethernet. So for example, for Rocky, you would need more. You would need PFC support. You would need headroom buffers and all of that stuff. So in UE, that's all optional. So it actually it's the true Ethernet in the sense that the switch you can take, there's a running joke in the consortium, it's like any switch vendor could basically come and put an Ultra Ethernet sticker on their switch and say it's an Ultra Ethernet switch, right? So that's going to be a management problem because some of those may be really bad, but that's a different discussion. So it's only at the NIC side. So it's really the endpoint side. Ultra Ethernet, the smarts are in the endpoint and it can run over 40-year-old infrastructure. Like that's one of the guiding principles. And so the protocol doesn't actually matter that much because as long as you have the same protocol at the same 2 communicating endpoints, it's not a problem because the infrastructure will carry it. And so that's the philosophy.
Yeah, might have a little bit different look here. First is that Rocky's ability to move data directly to the memory, CPU memory, GPU memory, has nothing to do with performance of the network. You can run Rocky on Wi-Fi if you want to, right?
Yeah. But it needs to be lossless.
The second thing is that all the aspects that are being brought into lossy in order to support lossy, including trimming and SACs and things of that sort, in order to reduce the penalty of dropping packet in UEC spec, for example, completely valid to RDMA, completely valid to Rocky. So you can actually you can use the same trimming, the same element, and you have a great Rocky running on lossy. So it's not one versus the other, essentially, and the packet format is not really important when you look on what is the capability of an infrastructure. Regarding Ethernet, or the multiple flavors of Ethernet, first, one difference is that NVLink is something that exists. Okay, it's in the 5th generation. Every generation you add stuff, assuming that you're going to define a protocol and its 4th generation is going to be the best ever created, have failed over the years. It's not possible. Okay, you need multiple generations in order to actually tune something, and that's what NVLink brings. Now, NVLink doesn't just bring its protocol, it's also bring the entire infrastructure that was built in order to support that stuff. Now, you had a good question, but there's multiple specs being created now, right? In multiple places. There were consortium in the past that tried to do one spec that fits all. None of them exist today, in a sense. And it could be because when you look on AI infrastructure, which drive a lot of that work, right? There is very large systems being deployed, and those systems are huge and cost a lot of money. You're talking about billions and huge amount of money being spent there. And the people that build those data centers to run their applications want to have those tuned to their frameworks. Okay, if you pay billions of dollars, you cannot just run something general purpose. And therefore, there is a good chance that you will see different protocols being out there. And every large entity will have its own protocol because they want to make sure that their infrastructure is optimized to the detail. Okay? So I'm not sure about convergence. I think there are going to be multiple versions, and we're happy to support multiple of those. Okay? So we support a lot of elements that our customers need.
Okay, thank you.
Also, may I stop the question from the audiences? And so that I have one question, maybe to the Torsten. So the Ethernet actually has a very long history. When I studied the computer science, for example, more than 40 years ago. But then Ultra Ethernet is something different from the new technology compared with Ethernet. Yeah. But also you have some backward compatibility or something, because your Ethernet is Ethernet. So my question is that InfiniBand is originally designed, in my understanding, that for the cluster computing and nowadays the HPC and AI, so that many of the hardware and the software protocol and everything is tuned for the HPC so far. Now it's focused on the AI. So what Ultra Ethernet learned from the history of the InfiniBand for 20 years and how to improve or correct some problems? So what do you think?
Quite a lot, I would say, actually. It's like, InfiniBand was a great success. I think it's a great product. It's a great product at its time. It was driving the future of, I mean, if we wouldn't have InfiniBand, we would probably not be where we are today, because Ethernet could have not delivered it in that time. But now the question was, can we take all the benefits that InfiniBand delivers today, like this RDMA, the semantics, and all of that stuff, can we put it into Ethernet in a way that's not just InfiniBand strapped on top of an Ethernet packet and then just hope for the best with the underlying protocol, but really integrate the two. That was the purpose of the forum. So we took all the learnings. It's not just InfiniBand, we also took learnings from other interconnects like portals and various existing interconnects, like HPE is involved, so X-Cray is in there. And NVIDIA also contributes ideas. And so it is a learning experience, and it is going to just be an opportunity for everybody, including NVIDIA. Yeah. Actually, I see this as a big opportunity that we could flatten the market and have a true competition like MPI was in 1995. Like MPI came out, and then suddenly, I mean, DK knows this best, suddenly everybody was converging, all this flurry of stuff went away, and it was all MPI. And now we hope to do the same with Ultra Ethernet, and then all the vendors can compete, and I can plug together a Mellanox, I apologize, NVIDIA NIC, I have to get this out of my head, it's really hard.
Me too.
NVIDIA NIC together with a Broadcom NIC, and they will actually be able to talk. It's impossible right now, there's no way. I mean, both have rocky products, but there's no way that I can hook them up and they will actually talk at a reasonable performance.
I see.
Today.
So you got any comment for their successor or no, I mean the follower?
Yeah, no, I think InfiniBand is still the gold standard. You know, Torsten just put it aside, but
no, I didn't put it aside.
There's a good amount
today,
of InfiniBand there, and it's cool, by the way. We built both InfiniBand and Ethernet, and Ethernet protocol. You know, if you take multiple devices running Ethernet protocol, they will communicate and interoperable fine. You know, you can have mix of switches and mix of NICs, and there is multiple rocky flavors of infrastructure out there that you can connect and mix and stuff like that. I don't agree that there is no competition. There is a huge amount of competitions, and you can see the variety of networks on the top 500 list, which means that there is a good amount of competition out there. That's one thing. The second thing, AI like HPC, because you want everything synchronized. I don't believe that someone's going to build a data center and is going to do a mix and match of multiple elements inside of a HPC or an AI data center. People don't use different kind of GPUs or different kind of CPUs and just create a zoo. It's a supercomputer, and a supercomputer actually going to have the same flavor across the data center. And that's what you want to make sure, when you want to focus on that, to actually deliver the performance that you want to deliver. Now, we're happy to support multiple flavors of protocols. NVIDIA is part of UEC, for example. We are part of the technical advising committee for UEC. We contribute the verbs interface into the software working group. So we do contribute to a lot of consortium, a lot of work, a lot of specification, and we support multiple of those, and we'll continue to support whatever our customer needs. That's why we have InfiniBand and we have SpectrumX, and there is NVLink, and there are going to be multiple elements in the infrastructure to make that a supercomputer.
Okay.
May I disagree on one part? I disagree on the supercomputer piece. While I agree that most people today are deploying supercomputers, but you mentioned yourself that you want to push, or what we are observing is that the data center becomes a supercomputer. If you look at any mega data center today, it is a zoo. It just is a zoo, because the lifetime for these things are very long. Not the training data centers that are deployed in the last 3 years. They're very homogeneous, I agree. But wait until the incremental deployment starts, and then we do inference and all of that stuff all over the planet. And that's these specialized data centers, of which there are dozens, I agree, but there are thousands, if not tens of thousands, of general data centers that will need high-performance interconnects for serving AI workloads, for training smaller AI jobs in the future. And this will be the zoo. The zoo will come.
Okay, thank you.
Just
10 seconds. I want to have a last question to DK, so that 10 seconds.
Yeah, just quick one. First, inferencing is already here.
Yeah.
Okay, a big portion of AI
in
is
a zoo.
Inferencing, it's not training. And inferencing data centers are homogeneous. Because inferencing, actually have even more load on the network. It requires much lower latency.
You just need local networks.
And stuff like that. So since we are part of a lot of inferencing system being built, I can tell you what is happening and what we see that's happening on our infrastructure.
It's not scale out.
And therefore, there is an homogeneous design.
Nobody does inference on scale out. Nobody does inference on scale out.
The second thing, you might be surprised. The second thing is that it's great to create protocols and specs. It's great. The implementation of those will be different between different vendors. And the implementation of those will determine the performance that you're going to get. And therefore, even if you build inferencing and training and there is one spec or one protocol is being used, still people would prefer, in our perspective, to actually build in homogeneous systems. Now, if they would like to have different homogeneous systems being connected together, that's fine. And that's great. And this is how things are going to connect. But this is what I believe, I think, and obviously we'll see what's going to happen.
We'll see, yeah.
So sorry for running that, but then last question to GK. So what you most expect or hope for the as a system developer, a system software developer, for the both side of or every interconnect?
Yeah, I mean, as I said, we have been following the trend. Every time some new technology comes, new features come. We are there to take advantage of that from the upper layer and give it to the end users. So that's what we have done. We started with InfiniBand, we moved to Rocky, and then if the newer Ultra Ethernet solutions will be coming, we can implement on that. We have done that with the Slingshot. I showed some of those numbers. So our end goal from a software perspective is that we want to reach almost like a bare metal. We want to deliver the best performance to the end users. And when I say end users, it could be HPC, AI, big data, any one of those.
So are you ready for the Ultra Ethernet ready MBAPIC system or something? It still is not on the product, but some discussion or a concept.
Which one? Sorry, I didn't.
You're focusing on the Ultra Ethernet implementation of your MBAPIC software stack in the near future. Are you planning to have some design or ready for that, anything? If the hardware is really cool.
Yeah. If the hardware is ready, we are always looking for better hardware, novel hardware. Those are our for our students and all, those are the research topics. We just jump in. Anytime there's some newer hardware, we are eager to try those out.
Okay. So let's discuss when the real product comes and for the second round of the fight. So I'm sorry for running out the time, but fortunately, there is no blood for anyone, so that is my biggest purpose to moderate here. So sorry for the running out of time, but I really hope that you enjoyed our discussion here. And thank you very much for the three panelists here, and especially that Torsten is so busy here because you are a PC chair also. But anyway, they all the kind very important and busy persons take time for their panel. And thank you very much for joining to this morning panel. And I really hope that everyone enjoyed that. Okay, thank you very much for joining.